The extreme physics.
All right, let's take a look at some more Newton's second law problems. Here we got Zach, whose mass is 80 kilograms, is standing on a bathroom scale in an elevator, descending at 10 meters per second. The elevator takes 3 seconds to brake to a stop at the first floor. What does the scale read before the elevator starts braking? And what does the scale read while the elevator is braking? All right, why don't you give this a try?
Pause the video now.
All right, I'm going to give it a try now. I have Zach. He's in an elevator. It's going down 10 meters per second. Well, we have two situations. Here we have 0. Here's the beginning situation where Zach's going down at 10 meters per second, right? And then we have another situation where the free body diagram's not going to really change. Well, the drawing's not going to change anyways. So here he still has a downward velocity, but he's braking to a stop. So he's going to have an upward acceleration. All right, so let's draw our free body diagrams. So our free body diagrams are going to be a little bit different. All right, I got my coordinate system like this because we have an acceleration that's up and down. The velocities are up and down, so that's where we're going to do that. In this case, we're going to circle the object of interest. Notice I didn't even bother drawing the elevator because Zach is not interacting in any way with the elevator. So the bathroom scale is pushing on him, and that's providing a normal force like that. There's the scale. The scale reading. And then downward we have the force of gravity. So that's pretty straightforward. Fg equals mg. What was the question? What does the scale read? So what's the normal force equal? All right, well, he's going at a constant speed, so the vector sum of the forces equals 0, and therefore the forces in the y direction also equal 0. So the normal force minus the force of gravity equals 0. Normal force up, force of gravity is 0. So the normal force equals the force of gravity, or mg, which is, what did they say, 80 kilograms times 9.8 newtons per kilogram. All right, 784 newtons. That's his weight, and it is the normal force. And there you go. All right, let's see what happens. So he gets in the elevator, he's going down, and then as you approach the floor, I don't know if you ever experienced this, where all of a sudden you feel heavy, you're just getting to the bottom, right? Our free body diagram is a little different. His weight is going to remain the same, that's mg. This is the approach I'm going to take in this class. You're going to do some reading tonight where the author is going to call anything the scale reads as the person's weight. So in this case, his weight is changing. I don't agree with that. That's not what we're going to do. We're going to say weight equals mg. The force of gravity is his weight, and the scale reading is just the scale reading. That's not what your author likes to approach it. There's different schools of thought. That's the school of thought I'm going to use. All right. Anyways, he's accelerating up, so therefore there must be an upward unbalanced force. So the normal force must be larger. Now I didn't draw my y-axis. See, we're accelerating upward because we're slowing down. Sum of the forces in the y direction equals not 0. Mass times acceleration, right? Sum of the forces equals mass times acceleration. This is accelerating this time. All right. What do we have? We have the normal force up minus mg down equals ma, right? Normal force up, the weight down. So the scale, which is the normal force, equals ma plus mg. Now, we don't know a. So let's see. I guess it's going to accelerate at a constant rate. They don't say anything to the contrary of that, and I guess we would have to assume that, otherwise we couldn't solve it. So I guess we have to do some kinematics to figure out what's going on with the acceleration. So he starts off at going 10 meters per second, and he's going to stop, because he's going to stop on the first floor. And then it's going to take him 3 seconds. So what's his acceleration? Well, that's pretty straightforward. Acceleration equals delta V over delta T. Average does anyway. So that's V1 minus V0 over delta T. V1 is 0 minus 10 meters per second. This is actually a negative 10 meters per second because he was going downward. Right? So minus a negative then, all over 3 seconds. 10 divided by 3, and that is positive. We have an upward acceleration, which is exactly what we were suspecting. So what do we have here? We have the normal force equals ma plus g, 80 kilograms. 80 kilograms. 3.33 meters per second squared plus 9.8 meters per second squared. All right, let's see. We got 1050 newtons. All right, so he feels heavier when he's braking, and I would expect that. That's what it feels like when you're braking in an elevator. And it's not ridiculously heavier, though. It's not enough to break his legs or anything like that. So, because he's holding up 784, and now it's 1080. That seems reasonable. All right, let's try a little more challenging problem. Otis gets in an elevator on the 50th floor of a building. All right, 50th floor. Maybe it's a tall building. I would imagine there could be more floors up, and there's definitely more floors down. And steps on a bathroom scale. Oh, that's convenient. The elevator begins moving at t equals 0 seconds. The figure shows the scale reading over the next 12 seconds. All right, there it is. Completely describe the motion of the elevator during the 12 seconds of the ride. Calculate the maximum speed of the elevator. What is Otis's weight?
Pause the video now.
0 to 2 seconds, and then this is 10 to 12 seconds. All right, so we have, it looks like we're going to have 3 different free body diagrams, but either way, this is what the drawing looks like. He's just standing in an elevator, standing on a bathroom scale. We don't care about the elevator itself as far as analyzing Otis. I guess the question is, why don't we analyze the bathroom scale? And it's because we don't know a lot about the bathroom scale. So we know more about Otis than the bathroom scale. So we're going to actually analyze Otis. There's Otis right there. All right. So from 0 to 2, here's a free body diagram. And you really need to have this down to understand what's going on. You have to picture what's going on. Free body diagram is going to kind of tell you that. So, all right. Now I could tell here, like it said, like at time 0, the elevator has just begun moving. So at this point, it's accelerating, right? Just started moving in 0 seconds. It's accelerating at this point. So this is not Otis's weight here. Okay, so I know an elevator works. It accelerates for a while, then you go constant speed, and then accelerates again at the end, right? You're either speeding up, and then going constant speed, and then slowing down, going up, or you're speeding up, going down, going constant speed for a while, and then slowing down as you reach the bottom. So right here between 2 and 10 is going to be Otis's weight, right? That's going to be where he's going at constant speed. That's how elevators work. They go at constant speed during most of the trip. You can't even tell you're moving, except things shaking around a little bit, maybe. All right, so at this point, from 2 to 10, the scale's pushing on him. We got the normal force. And then we have his weight downward, right? And those are equal. That's like when you're in your bathroom scale in the morning. It's actually measuring the normal force on you. That will be the weight as long as you're not doing this, like this, or the earthquake going on, or you live in a real bouncy house that's constantly bouncing and you have these things that cause it to go rock up and down all day. Most people don't have those houses. Now, what's different in the beginning? The beginning, like his weight is always going to be the same. He's always got the same weight. I like that. That doesn't change. 10 seconds to 12 seconds. Here again, his weight's the same. Boop, boop, boop. But now the force has dropped. The upward force has dropped. Right here, it's lower. Right. Here, it's higher. Yeah. All right. The equations are going to be the same. It's just we're going to get different information. So it looks like here he's accelerating upward. I can tell that, right? I can tell that. We got an upward acceleration here. We got zero acceleration here, and we have a downward acceleration here. All right. Well, if he starts from resting as an upward acceleration, he must be moving up. So starts moving up. Starts going upward. Then up at constant V. And then slowing to a stop at a higher floor. All right. So this is clearly a building with more than 50 stories. All right. I guess we should calculate the acceleration. If we want a complete description, sum of the forces in the y direction equal mass times acceleration in the y direction. So normal minus mg, and we're not going to use mg, we're going to use fg because we have forces here, equals mass times acceleration in the y direction. All right, let's see what that gives us. 1.225 meters per second squared. All right, that's what I get for acceleration. We calculate the speed here. So the elevator starts v0 0 equals 0, and then I'll call v2. I just call that 2 at 2 seconds. What does that equal? Well, the acceleration is 1.225 meters per second squared. I'll carry extra digits through the intermediate calculations, and then we'll give our reasonable sig figs at the end. And then that takes 2 seconds. 0 to 2 is 2 seconds. 0 to 2. All right. So acceleration equals delta V over delta T. That's average acceleration. Equals V2 minus V0 over delta T from 0 to 2. All right, that's 0 to 2 also. What is V2? V2 looks like it equals acceleration from 0 to 2 times delta T from 0 to 2 plus V0. 2.45 meters per second. So that is actually the velocity from V2 to 10. So that would be the maximum speed of the elevator. Otis's weight is 800 newtons. And why don't we calculate the acceleration at the end? So this is really the same relationship as we had before. We just have different numbers. The normal force in this case is 700 newtons. 700 newtons minus his weight, which is 800 newtons, divided by his mass, which is his weight, which is 800 newtons, times 9 divided by 9.8 newtons per kilogram, which I will just put up here instead of dividing by that. Negative 1.225 meters per second squared. All right, there you go. Hope you did okay on that. And I hope to see you in class tomorrow. Have a good one. Bye.
Extreme physics.